That's all I'm going to say, how much I'm going to say about this. But today, we still want to finish the introduction of the new concept that I have started out. I pretty much laid out the foundation. So but let's recap what we have talked about last lecture. And then the Friday we'll finish up the introduction of the key concept of this week, which is the chemical potential. What do we mean by that? So we have basically, just recap, we have used ideal gas as an example. We talked about two situations. Well, at the very beginning, well, a gas A and B are separated, and the molar Gibbs energy of each can be just calculated like we normally defined before. So that's the situation. So we have, this is the beginning point. And of course, you can always calculate the total Gibbs energy by basic definition. Okay, so then we introduced a very common phenomenon. We have talked about this a couple of times. That is, now we remove the separation. So now the separation used to be here, now it's gone. So basically, gas A will transfuse over both chambers, and so is gas B. So now we know. So basically, we know after our discussion, what is the total? We actually don't know. So basically, we know the total Gibbs energy is still equal to some form of the whatever the gas A will contribute, except throughout discussion last time, we found this very intriguing phenomenon, right? Naturally, we go, oh, this would be the same. But we know it's not the same because this thing rushes over. It's spontaneous. So from our class discussion, we have arrived at a point where we realize this got to be different, right? So that's how we ended up. So I'm going to just review what we have arrived at. And soon, hopefully, you'll see this is quite interesting and also very, very important for us to lay out the foundation, a new concept that we will deal with a lot about Gibbs energy. So from last time, we realized, wait a minute, so basically, this is different. So the total afterwards and total at the beginning, we actually did something as we calculated. It will be NA-RT natural, or the molar fraction. So you can go back to, hopefully you already see the notes, or if you don't, it's in the lecture notes of last lecture's PowerPoint. So, and we have, so each of these definition, the molar fraction is the number for A ideal gas and B ideal gas, the molar fraction of B and B. So that's basically out of the total amount of ideal gas in the chamber, what fraction is A, what fraction is B. So are we still together? Any clear? So this is everybody recall, and hopefully we're on the same page. It's pretty important. Well, I want everybody, don't try to write too much, think about more, because I'm taking it, thinking about getting you to, if you, any of this just kind of, wait a minute, I don't think I remember that was the case, just you talk to me, because I want everybody to be thinking along with me rather than trying to copy it on the formula, because the formula, you have two places to find the formula. One is on the PowerPoint, and one is at table. It's much more important for you to follow the flow of the thinking. And that's something that I'm emphasize a lot in teaching this course. So, so if we plug in the left side, we get a very interesting phenomenon. We're like, oh, actually, basically, what happened is the new Gibbs energy. Right? This board is not working today, but it will be the old one, then plus some interesting term. And we all know, because this is a fractional, so they're less than 1, so this will be negative term, so the right hand is negative. So we know the Gibbs energy change is negative, so this one is spontaneous, right? So everything, everything is consistent what we have talked about so far. All good? Yeah. Okay. So now if I put back this thing, then you'll see we'll get a very interesting phenomenon. Like, well, so we put this back in, it'll be Na, originally molar Gibbs energy of A, and then let me put this right over here. And then it'll be Nb, molar Gibbs energy of B, Okay, I'm going to stop the mathematical symbolism because I don't want us all get lost. So I have to pause here, think about what do we mean, what this equation really trying to tell us in terms of a principle or something that you can generalize, or how we're going to use this to go back to explain other phenomena that later on we're going to use this. So what does this whole equation tell us? Now initially I use something that we have learned, right? We know this is spontaneous. I mean, it's a little bit of mind teasing, because you would think nothing really I didn't do anything. No work, no heat is done, and a gas didn't get leaked out. I have this much Gibbs energy, and you're saying that I yanked the separation out, and my Gibbs energy changed. What? I mean, it's like, it's almost violating the conservation of energy principle, right? It was almost like violating the first law of some dynamics. I didn't do anything, and then I lost some energy. What happens there? So that's why we need a second law. So the first law is not good enough. So that's one thing I want to impress you about. That is, it actually touches up on what appeared to be a very counterintuitive experience. And that is what's going on here. So that first is counterintuitive. But then I didn't do anything, like I didn't trick you here, because I don't try to impress you by drawing a bunch of mathematical formula, but you would have to agree with me, since just don't go back. So that's something, so if you agree with me, then the thing we're driving here is translate this, you would never doubt about experience into a language that we will be using, which we have been using, that is the thermodynamics. So that's the second point I want to make. Now, okay, having said all of that, we don't just do the mathematical translation for the purpose of creating a mathematical translation, right? You would argue with me, why do we want to do this? I mean, this is perfectly understandable. If you want to use thermodynamics, I can say that's fine. So that's negative, because this is smaller than 1. This is negative, we're all good. Why would we want to do more? Well, the reason we want to do more is we have to think there is something interesting about Gibbs energy. That is, its actual value has something to do with the other substance is mixing with it. So we're entering a point to deal with a mixture. Up to the point in the previous discussion, we have focused on phase diagram, where we have a pure water, we have ice, we try to add pressure, we try to heat it up. Nothing is about mixing. Now, this is the first time we're starting to enter in a new realm in terms of our discussion about Gibbs energy, or for now, let's call it molar Gibbs energy. Okay, so that's the entry point of the discussion. That is, we realize when we have pure gas, if I add a little bit of, in the left chamber, if I inject a little bit more of this gas A, I increase the molar Gibbs energy by just that. Because it's pure, that's what it is. Whatever amount I add to it is it. Now come to here. In that mixture, I inject the same tiny amount. So here, well, this is still the system, except things get separated. If I add a trace amount of delta Na, so I increase the total by Na plus delta Na GMA. So whatever that is, I just increase that amount, right? But here it's pretty tricky. So wait a minute. So if I'm a Na become Na plus delta Na, what happens? So in the same chamber, I inject a tiny amount of delta Na. Now, except I have a bunch of other stuff around. Do I increase the Gibbs energy by the same amount, or less, or more? I see a bunch of head shaking, but those who did not shake head, can you raise your hand? Because apparently you disagree with that. Anybody who would disagree with this point? Asiya, what do you think? And do you know what the reason? So should we increase this amount or less amount, and why?
I'm not really sure about it. I wasn't here for 1 day.
So my question is, here I know if I add a tiny amount of gas A, I increase the Gibbs energy by whatever the molar Gibbs energy times that. In this is when everybody is separate. But here when I have a mixture, I inject the same amount of Na, except everything's mixed. And the amount of molar skirmish of the system will increase by the same amount as before, I add the same thing, or not. Because, look, for here, all I'm changing the value is Na become Na plus a tiny little delta Na. Kalia?
Would it increase less because you're adding to, because going back to the mole fraction, that would change what you would subtract from each of the total.
You said it right, but I wanted you to be someone to be mathematical language. So you got it right. You're saying the right thing, but I want someone to be more. Because I know the class is uncomfortable with partial derivative. This is my attempt to make partial derivative demystified. Because we hate partial derivative. Let's not use it, but we are actually doing partial derivative at the moment. So I want someone else to chime in a little bit on this one. So clearly, the way I'm increasing Gibbs energy in this situation is not as much as this. Johan?
So if you're increasing, let's say, gas A,
yeah,
then the partial fraction would be less than 0, or sorry, less than 1, right?
Yeah.
Then if you have a natural log of anything less than 1, that'd be negative.
Basically, that's what it is. Yeah. So I mean, it's actually not. I didn't mean this one to be very complicated because I know. So here, let's try to write out what's going on here. So you have Na more, and then plus delta Na more. So this is the net increase from the beginning, correct? This is what we're start. This is the new one I'm getting, right? Claudia?
This is also plus NB.
Yeah, the NP does not change.
Yeah. But that's also included in
the
total.
Okay. So plus.
I just wanted to make sure.
That didn't change. Yeah, plus B fixed.
Yeah.
And here, Johan basically set it up. What happened is you, of course, NA, GMA, and delta NA, GMA, and then you have NART. This is the original, but also you have delta NART, natural. And this guy is always negative, so it actually brings it down a little bit. Okay, this side is fixed. Okay.
Is that side fixed though? Because you change the
That's
threshold.
that's the derivative issue. So I can say that so infinite small, so B as if it didn't change. That's always the trick
It's-
of being derivative.
Okay.
Yeah. Austin?
What's B?
What?
B, you said, or,
Oh, so when I have this side is fixed, so I inject something so tiny, so the B, the amount of B, the B fraction or whatever, it was, not even A's fraction was considered to be not changing. Otherwise, I can't do this. Basically, this is the kind of situation where you do derivative. You make a tiny change, you assume the main constant is still the same. So we did that a lot. So here is, just like Johan said, basically every time when you do this, your actual slope, because the slope, for this one, the slope, so when you think about the Gibbs energy change, and this is the matter, and you got a straight line up, okay, and that is, okay, and here, everybody fixed, B is fixed, Y makes tiny change, the slope, total Gibbs energy over the NA is not a straight line. It's actually keep curving down. As well, no, actually it wasn't curving down. So actually, because if you have NA fraction up, it should be like obviously going up this way because every point is changing. It's not the molar fraction. If the molar fraction is higher, the amount of A is higher, and then it will have a more fraction, then this number is bigger. But if the molar fraction is smaller, A and A is this amount, then this is a smaller, and then its slope is smaller. So it can't increase as fast as, how fast does it increase? It depends on, at the moment when you add to the same solution, how much A is already there, what fraction it's already occupying. So it's actually a changing value. Makes sense? Kelly, you look puzzled.
What is the actual fraction for delta
So
NA?
so basically what I'm saying, so let me actually try to rewrite up here. So the slope is a changing slope. And the reason it's changing slope is because the slope is equal GMA when it's pure plus RT log fraction. Think about, because this is where NA GMA plus RT potential log. So you put them together, and that guy's changing. That guy's changing. It does not always bring up by the molar Gibbs energy. It brings up the molar scalar energy, but I subtract by whatever the molar fraction is going to. So its slope got bring down by this molar fraction. Virtually what Johan is saying. I'm just trying to add a little bit extra explanation to do because this is what we're doing about partial derivative. Austin?
so then that's because the molar fraction can never be larger than 1. That's why ln is negative. So it will always be less than the pure.
Yes, you basically get ahead of me. So I'm going to make that point very quickly, but that's actually a very good observation. And so that's, I'm trying to get right now. So the point is that, now everybody's still with me. Don't try to rush right down stuff. Let's try to join the discussion. So what did we see here? Something very intriguing is going on. First, so we have said all of that. We noticed that now within the mixture, we have noticed that the contribution of each gas to the total Gibbs energy, or another way to say it, per mole Gibbs energy the gas is contributing to the system, is no longer the same when it's pure, when there's something around there. And per mole of Gibbs energy contribution for each of the gas to the whole system has been devalued by whatever the mixing effect of the other gases around. So this is the per mole contribution of gas A to the total Gibbs energy. Now this, in the mathematical term, is actually called partial derivative. I mean, there's nothing funny about it, nothing mysterious about it. It's just, every time when I do this, it'll probably be too much mouthful to talk about like this. So the mathematician just said, okay, well, we just had all this discussion, right? We all in the class, we decide. All the discussion we have made, let's just write a little symbol. So next time we don't have to spend this much time to write it all out. And we just say, oh, the total Gibbs energy. They don't use the D, that's a normal. So this partial basically means the total Gibbs energy. Change of the, with a tiny amount of A change, when I try to fix, and T and P and also other guys don't change. So when that happens, this virtually is relatable to when it's pure. Except in the pure, this is a constant, so we can always write it as it is. But in its mixture, we can't do that, right? We basically, we fix it, so nothing really, this right side is constant, it's all gone when you do derivative. So what the whole thing I've been talking about is that I'm changing tiny amount of A, and then when everything else gets fixed, temperature, pressure fixed, B is fixed, and I realized this is intriguing because it becomes when it's pure, so I can always put an asterisk on it. That's when it's pure. That's molar one. Then plus RT. So this is the end result of the whole discussion. That is, every time when I mix stuff, I have the result of this is I kind of created a situation where the molar Gibbs energy of a particular substance in the mixture, careful, is no longer the same as when it's pure, and then therefore it's dropped by the mixing effect. Aaron?
How do we mathematically deal with the changing molar fraction?
I just said, so I inject a tiny amount of.
Yeah, but I'm saying if you want to do a big change, do we not do that?
Then you have to integrate.
Ah, okay.
Yeah, so that's the same way. This is so important. I'm going to just stay here until everybody started to light up rather than look at me with that inquisitive pardon face. Diego?
And I thought we were keeping like all the NB parts constant, so are they not included in this?
Yeah, when you do D something, do something,
no,
all the constants just disappear.
okay.
They don't change.
And the pure just doesn't have the second part.
But
The pure one is just no RTL.
when you have pure, yeah, you don't have this thing. So the pure one basically, if it's pure, basically is DG, DA, and A. That's a G molar A. And that's basically the one we're doing over here.
Yeah, makes sense.
It's very important. We have to get this. So we got to have to agree with on this one before we move forward. And then the next important concept will get to the key question part. Jerry?
Yeah, the star that you put, is that the pure?
Yeah, I forgot. I'm actually always afraid of using things because I think sometimes you start, sometimes people use a little circle because standard state, and if you see the notes, so it's more important for you to know the concept. And if you go to different textbooks, sometimes they use star to represent the pure state. Sometimes they draw a circle, put a little cross on it, called that reference state. Let's not worry about for the moment. Let's in the context of our discussion at the moment, we're talking about when the gas is pure, but later we'll come back to address this point.
That equation is for pure.
This equation is for a mixture. This equation tells me, the equation on the right side, in this mixture, for the gas A, if I try to increase its Gibbs energy by add a tiny amount of matter, gas A in it, I'm not able to increase the molar Gibbs energy as I normally do in the pure gas, but rather I can only increased by whatever I normally do in the pure case, but have been discounted by whatever the molar fraction is. How? Okay, so everybody on the same page? So is this still kind of so weird that you don't feel comfortable? Raise your hand if anybody. Nick, Natalie? So in which aspect? Like what part? This makes no sense.
What was the mathematical reason again? I think I understand the concept why a small injection is going to have a less increase in the mixture than in the pure, but I just don't understand the math reason why.
So the math reason is if we're, okay, let me actually rewrite this a little bit, so it'll probably help. So if I actually write the G total equals to NA plus G MA plus RT plus fraction A and plus NB G over A. No, so I kind of bracket, right? So, right now, okay, so this is referred as a pure state, okay, at the moment. If I want to be more vigorous, I just should start not confusing you by having all of them. So this refers to pure, so you don't really, when I was, so.
Sorry, is it NB G molar B or A?
Oh, yeah. Thanks. So, okay, so for Nick and Natalie, so let's say this is a equation of, think about this is we have a two-element equation. This is the X and that's Y, right? So these guys are just, so I'm trying to monitor how these guys change over the X or Y. Now I'm fixing Y. So everything else on the B term, fixed B term is just not changing. So basically I'm trying to watch how this guy is changing over this X. And so the slope of it should be on this term. Make sense? So basically what I'm trying to describe in here is that how the Gibson has changed over a tiny amount increase of A when everything else is fixed. I'm only increasing A. So that means this is the slope that I'm trying to, so this is the changing rate, the speed. Now if I come back here, you probably will not be arguing with me. So let's say in this situation, this is a simpler equation. I'm trying to increase A in this system by a tiny amount. Now, there will be no doubt you'll say, oh yeah, so the slope is this guy, isn't it? So the same is here. The only reason is the slope changed. It changed from the pure A, weirdly enough, because we did all this derivation last lecture, that it had this, we noticed the slope cannot change as fast because it has to be put in RT L and XA. Well, I'm not repeating this. How we get here was last lecture's work. Right? So because of that, we realized the changing rate as you increase it, a small amount of A is no longer as pure, but rather the pure increase rate being dragged down by the mixing effect, RT natural XA. Makes sense? Okay, so I didn't do any more mathematical. So here, from here to here is just try to write a strange symbol that you're not familiar with. But if you understand what I was saying, this is just an easy way for people to we probably don't really talk about this. So sometimes we give this a new kind of a molar Gibbs energy of A, and sometimes a much more common expression is the chemical potential. Okay, so why do we call this chemical potential? Now, before I go forward, any other question about, let's not worry about this. So, we know molar Gibbs energy is very powerful, useful when we actually predict something is going to change from phase A to phase B, or something's moving from point A to point B. We compare the molar Gibbs energy high, right? A substance always go from molar Gibbs energy of higher ground to molar Gibbs energy at lower ground. So we already established that. We have tested that on phase transition very well. But that only applies to pure substance. But in biology, in chemistry, we deal with mostly solution. So all the things we said is highly limited. We have all the principles established, but we can't really use them. So when we use them, we actually deal with mixture. But it is for that reason we spend all the 2 lectures basically try to introduce you when there's a mixture, what happened to the molar Gibbs energy? Well, first of all, you know molar Gibbs energy decreased. Keep in mind that. When you have a mixture, if a substance is in the pure form, and then when it gets mixed with something else, if nothing else changed, you know that substance molar Gibbs energy decreased. This is the evidence. Everybody agree on that one? Yeah, Kalia? Does that make sense?
Yeah, I just
Yeah,
got lost
okay.
a little bit.
Yeah, exactly. It's a little. So I'm trying to, because I want to make sure that if you are looking puzzled, then I think a lot of other people do too, because you're closest to me. I can see your facial expression clear. So that's one thing. The other thing, so when a substance gets mixed with other thing, its molar Gibbs energy contribution to the system will be decreased compared when it's pure form. That's the first sort of intuitive statement come out of this whole mathematical derivation. The other thing is it's no longer constant in a way, because if you have a pure substance, when temperature pressure is all fixed, the molar Gibbs energy is constant. Whereas here, it really depends on what you're adding into. So clearly, if in the solution you have different composition, the per mole Gibbs energy, you are going to cause the change or affect when you add a chemical into a solution, and its per mole contribution to the total Gibbs energy depends on the actual molar composition, which is that term. So, okay, now if I put the 2 statements together, what does this really mean is the molar Gibbs energy of a solution or a mixture has something to do with its intrinsic molar Gibbs energy when it's pure. That's the reference point. And how much does that guy's contribution or mixture in that solution. So in a way, we can always call this molar Gibbs energy, but because it's so powerful, so useful, there's a special dedication name for it. It's called chemical potential. So chemical potential virtually is just molar Gibbs energy in the mixture. So I would just put it this way, and it always equals to when it's pure plus whatever that substance. It's called these A. So if you have a substance, that A substance has a pure form, so it has a molar Gibbs energy. So let's just put a suffix mole behind it. Now it has a pure form, so it has a molar Gibbs energy. We know that constant. But when it's not pure, its per mole contribution to the system is degraded. Yeah, we didn't. Everybody. So what that means is when something has a lower concentration, its molar Gibbs energy is lower, right? Wouldn't you agree with me? So we already know this what's going on. We'll come back on Friday to see whether this statement makes any sense. All the stuff we're doing actually is useful or not. Renee?
Yeah, so I understand like the main concept. My main question is, so NV is fixed. You're changing NA very slightly. Wouldn't that also change the mole fraction of E? Or are you assuming XV is not going to change?
Okay, so in this whole situation, if we say fixed NB, the right side don't change at all.
Okay, so XV, okay.
Yeah. So that's why we say. And then even fraction A won't change. We just change tiny amount of A. So we're basically saying that in the current composition, if I add infinite small amount of A, how much per mole Gibbs energy I'm going to contribute to? This is a common practice when you do derivative. You change the A, X, you have added that X, but you think X is not changing. So that always kind of always throw people off at the very beginning. So wait a minute, I'm adding delta X and you call X not changing. Well, that's basically, because that's why you call delta X is infinitely small. So in this case, if I add infinite small amount of A, and B, molar fraction B and molar fraction don't change. Okay. Now, so this is very important. Okay, let's go back. Let me repeat one more time. So all this experience here, combined with thermodynamic principle and some mathematical formulation, led to a very useful concept, which I want to repeat multiple times. That is, when you have a mixture, the Gibbs energy, the molar Gibbs energy of that substance in the mixture is no longer the same as when it's pure. And it deviates when it's molar Gibbs energy from the pure form by whatever the concentration of that is. Obviously, the higher the concentration, the closer it is to its pure form. Eventually, when this molar fraction gets to 1, you get a pure form, you're good to go. You're back to normal. Yeah? Renee?
Yeah. I guess maybe for future lectures, I think the concept, we mostly understand it. Do you think maybe you could provide us with a few numbers every now and then so we can see a problem, to see the actual
Number calculation?
Yeah, like a little one, like just for future.
Okay, so I'll keep that in mind on Friday, so go back. But it's very, very important for us to appreciate this concept today. So now, in the remaining minutes, I'll do some expansion of this discussion, then we will come back on Friday. So this one will be really quick, but you need to go back to think about a little bit more of this. So one of the very useful expansion of this is that if you go back to here, so use this as an example. The molar fraction of this basically will lead to, so I'm going to ask the class to really show this. So basically you have, say, if I have the total pressure in this mixture, so if you are wondering what I'm talking about, you better go back and review your Dalton's law. So when you have the two mixtures together in the chamber, if the total pressure is P, then the partial pressure of this one guy, gas A, is the molar fraction of the total P. If you're like stunned by that statement, then go review the ideal gas of the Dalton's law. Total pressure is P. The gas A has a molar fraction of XA. Its partial pressure is the total pressure times the molar fraction. Now that's the Dalton's. You can easily prove this point by using ideal gas. Okay. So what I'm doing here is then all right. So this can always be expressed the partial pressure divided by the pressure. Yeah. Okay, so that's good. So it gets really interesting point. Now, so here, the mixture of the partial pressure, all of a sudden when it's pure form plus RT natural log PA and P. This is even more interesting because you can see what this, you can think of when they are separate, on each side, on each separate side, the PA basically its own P, right? So when you separate the chamber, the partial pressure of the gas gets to the total pressure, but so this partial gas only gets to this point, gets its partial. So therefore, what does this really mean? When I have a gas, if I have a pressure at P, if I call that the reference point, that's the pure point. But I change the gas pressure into new pressure, I change the Gibbs per mole Gibbs energy. Now, if you're wondering about this, I want you to prove this point in a different way using this. So this is how we're going to end here. So prove above, use molar assuming T fixed. So this is the ideal gas, of course. So we will come back to this. So up to this point, I made a very strong statement on, well, I made a very important statement about how molar Gibbs energy in the mixed state is different from pure, how the molar fraction in the concentration format can be used to predict its influence on the molar Gibbs contribution. Now, we are getting to another point, because when we say, okay, chemical potential, what do you mean? So we always end up comparing with certain point. Now, in the chemical potential discussion, it's very important for us to know who are we comparing with. So in this formula, I have already used Dalton's law to show that because the pure state is when the pressure is P, but the new chemical potential of the gas when the pressure gets lower or gets different, and its molar Gibbs energy is different from the previous one by the ratio of the pressure. Now this formula does not need to be derived through this whole process. You can actually prove the molar Gibbs energy change of an ideal gas can always be expressed by this equation by using this formula to derive for it, okay? So by doing that, we'll make a very important point on Friday, that is, how do we set a reference point? Because if you talk about the molar Gibbs energy comparison, in the other case we use pure, it's easy. But when we have a concentration, we get into a big problem. We don't know what do you mean by a concentration. So we can always compare with the pure, but in the gas phase, how do we select a reference point for chemical potential? When you like the potential. So this particular practice, if you end up doing it before Friday, it'll be very helpful. So on the Friday, we will join on the concept of chemical potential and how to set a reference point. And in this case, the reference point is the pressure corresponding to the pure state. All right, so we'll continue that on Friday.